Hello, everyone. So now we're going to make a challenge analysis, and I will make a tutorial about today's task. So today we had a non-overlapping community detection task for a big graph. So the non-overlapping community detection is about graph coloring. We have a graph and we need to separate it into a set of communities, and every community must be they must overlap. Every graph node but must be colored by some color. So we have introduced a score which has two parts, the modularity part and the regularization part. The modularity is a well-known metric used in community detection, and it shows the degree to which the separation into community is good or not good. And we also introduced a regularization part, which will affect the size of the community, mostly the size. So it has a positive part, which is an average density of a community, and it has a negative part, which will block contestants from making very, very small communities. So let's talk more about modularity optimization, because this problem is, this part of the score is probably most complex. So modularity reflects the concentration of edges within community compared to a random distribution of edges between all nodes. So this concept comes from mathematics, and so the formula is very complex. However, we believe that for a 3-hour contest, probably it is not needed to understand the formula in details, and perhaps it will be enough just to get the general idea of the formula. So, and generally, maximization of modularity, when you want to do a maximization of modularity, it may be beneficial just to make a separation of graph into communities, and such that communities are dense inside and they are large enough. Otherwise, it might be beneficial to enlarge a community, keeping the density high. So, however, we also introduce the regularization part, which will keep you from making communities too large, and this is important. So in the task statement, we gave several examples of modularity score just to give you some feeling about this score. So if we have a border case where when every graph node makes a singleton community, the modularity is always negative. So please do not do like this. If we consider another border case when every graph node is put to one big single community, then the modularity will always be 0. And so the balance will come when you have some nodes grouped into community, and you should also take care about the size of this community. In mathematics, we have a theorem that says that modularity takes value from the range -1/2 till 1. So, however, it is important to underline that the maximal possible value of modularity may not necessarily reach the value of 1, whatever partition into communities you consider. And actually, for every graph, the maximal possible value of modularity is different. So, for example, today we had 3 graphs, and the maximum possible value of modularity for these 3 graphs is different. So the score will also be different for all 3 graphs, and we cannot compare it directly. So, for example, 200,000 score for one graph and 190,000 score for another graph cannot be compared one to another, because the maximal possible value of modularity is different. So modularity optimization is a hard problem. It is actually NP-hard problem, and we have an excellent result by Brandes and his team. So if we consider a decision problem given a graph G and some constant Q0, does there exist a partition with modularity higher than Q0? Brandes proved that this problem is NP-complete, and he used a construction that relies on the fact that all nodes of a sufficiently large clique must be assigned to the same community of an optimal partition. Actually, it gives us a hint how we potentially can solve this task. For example, we may consider clique detection or maximal clique detection, and we can use this as a heuristic to make initial partitioning of our graph. Even so, modularity is NP-hard, and restricted version of modularity optimization problem is also NP-hard. For example, for every constant k, we consider an individual decision problem, given a graph G and some constant Q0. Does there exist a partition with at most k communities with modularity higher than Q0? This restricted version, even though it looks easier because we restrict the number of communities, it is also NP-complete. So basically, modularity optimization is a computationally complex task. So we hope that today our participants could have come with some approximate solutions, some heuristical methods, probably. Of course, we do not have, we cannot give an advice how to solve this task because it is an optimizational type task. So there could be many, many approaches. However, we hope today's discussion will help you. So we have some mathematical facts about modularity. For example, we know that if you have a graph and if you have an isolated node, these isolated nodes will have no impact on modularity. Also, if we have a graph partition with maximal modularity, we know that it is not possible to have a graph node with a degree of 1. So if you have a graph with maximal modularity and if you have some node which is just connected by one edge, he must be colored together with the node he's connected to. This actually can be used as some kind of heuristic for local optimizations. Also, we know that if we have an optimal clustering, then every cluster can be connected. So, for example, if you have two disconnected components, we can assign different communities to both of them without losing the score of modularity. Also, we know that if a graph is made of a single k clique, then the optimal modularity is trivial, and actually it is 0. So just to remind, a k clique is a graph that has k nodes and all edges. So we have this formula of modularity, and from the very beginning, one can see that it has a summation over all communities. So by this definition, each community contributes to final score separately. So one may think that this is a local feature, a local score. However, it is not the case. And actually, modularity is a global feature of the graph. You cannot optimize it locally. So this makes this modularity optimization problem more interesting. And we have several unusual features. For example, one unusual feature of modularity optimization is non-locality. Consider a graph at the top. It has two communities. One is green colored, another is blue colored, and it is an optimal partitioning of this graph at the top. And the modularity value is given as 0.208. Suppose now we want to add one additional node at the right top, which is connected to this graph. But we have a mathematical theorem that if we have a node with degree 1, it must be colored the same as the node it is connected to. So we might think that we just need to put it to the same blue community. However, in this particular case, the optimal partitioning is shown on the right figure, and we have three communities here. So we can see that this modularity optimization is not local. We just introduced one graph node, but the color of a distant node has changed. Previously, we had a blue color node, and now it is green. So when you do local optimizations, if you, for example, move one node from one community to another community, it can also affect the other part of the graph. Another interesting theoretical and also practical feature is sensitivity to satellites. So at the left graph, we see a maximal click, and as I said before, its optimal modularity is 0. You must put all graph nodes into one community. So now we add satellites. By satellites here, we mean leaves, so some graph nodes that are connected to the click. And as I mentioned before, from the theory point of view, in this case, these new nodes must be colored the same as the main nodes. So for this particular case, the modularity is 0. However, the optimal modularity here is higher than 0. And if we add satellites, our community breaks into many, many small communities, which is very astonishing. Another interesting feature of modularity optimization is related to scaling. For example, when we have a small graph and we optimize modularity for a small graph, and then we enlarge it and optimize modularity for a larger graph, then the partitioning for small graph may change totally. So for example, if we simply double our graph with leaves at the left, we will have a value of modularity 0.16. However, the optimal partitioning here is different, and we need to just have 2 communities now. So by enlarging the scale of a graph, we actually make communities larger. This is an important feature of modularity optimization problems. It tends to return large communities. And this is actually one of the reasons why we introduced regularization. Because if you remember, in regularization, we give positive score, we give higher score if the density of community is high. So the density of community that has just 2 nodes is obviously higher than the density of large communities. So now we know that modularity takes a value from -1/2 to 1, and we also know that it may not necessarily reach the value of 1, whatever partition you consider. And we also know that for all 3 graphs, the maximal possible modularity is different. So we have a question how to judge about the maximal possible modularity value. Do we have theoretical results, or do we only have practical results in this area? Andrei Redgorodsky, who is professor from MIPT and director of MIPT School of Applied Mathematics and Computer Science, and also who is ICPC 2020 World Finals Director, together with his team recently published a paper regarding modularity of some distance graphs. This paper theoretically analyzes the maximum modularity possible for a family of distance graphs, also known as Johnson graphs. And Redgorodsky, together with his team, obtained several beautiful mathematical results in this area. So the distance graph is a family of graphs. It's not a one graph, it's a family of graphs. And the set of nodes is the set of all R element subsets of a range of numbers from 1 to n. And the set of edges is defined as pairs, where edges connect pairs of sets intersecting in exactly S elements. So we have 3 parameters, N, R, S. And we have beautiful theorems. Theorem 1 gives us upper bound on the maximal possible modularity for a given graph, and theorems 2 and 3 gives us lower bounds. So as you can see, there is still a theoretical gap between the upper bound in theorem 1 and the lower bounds in theorem 2 and 3. For example, when S equals to 1, the gaps it's a gap between the upper and lower bounds grows with increasing R. So the upper bound is asymptotically equal to 3/4. However, the lower bound decreases hyperbolically. So in theory, we have a situation when it's very hard to estimate the optimal value of modularity. And it's actually an open question and an excellent topic for a PhD work, in my opinion. So now we have a question, how to optimize this complex score. Modularity optimization is a well-studied problem, and obviously there are many algorithms. For example, we have a greedy algorithm and we have Louvain, which is a very popular approximate method. We have also spectral methods and others. So let's briefly introduce this approach, because in my opinion, this greedy algorithm and the Louvain algorithm can be implemented in a 3-hour scenario. So I think it's meaningful to talk about it. So the greedy algorithm, we start with a singleton partition. So every community, every graph node makes a unique community. As we discussed in the beginning, in this case, the modularity is negative. So we're now trying to increase it. We iteratively merge those two communities that give a partition with the best modularity. And after we process all nodes, we select the partitions that achieved the highest modularity as our final result. And we have an excellent theorem that if we use a greedy algorithm, there is no finite approximation factor. What's the meaning of approximation factor? For consider an example, we apply a greedy algorithm and we get some modularity. So, and we also have a maximal possible in theory modularity. So approximation factor is how many times our algorithm is lower than the optimal value. So there is a class of graphs on which the greedy algorithm always returns a graph with modularity 0. However, the optimal modularity is close to 1/2. So we can conclude that there is a class of graphs when the approximation factor is almost infinite. Another popular method is the Louvain method. And personally, I think that many participants might have chosen this method for their solutions. So the Louvain method is a very popular greedy community detection method created at the University of Louvain, Belgium. And it has two phases. First is a local modularity optimization, when small communities are found by optimizing modularity locally on nodes, and then communities are aggregated. So each small community is grouped into a community node. On local modularity optimization step, we start with singleton communities as well. And for each node, the change in modularity is calculated for removing this node from its community and moving it to a neighboring community. So this process is illustrated here at the left. We see that we start from a gray color graph and we obtain a red, green, blue color graph. So by some local procedure, and then we have an interesting step that we group all nodes that were colored similarly. For example, all green nodes are grouped into one super node or community node, and all blue nodes are grouped into one blue super node. And we make a graph based on communities. So links between nodes of the same community are now represented by self loops, and we have the number showing how many links inside community we have, and links from multiple nodes in the same community to a node in a different community are represented by weighted edges. If you recall the formula about modularity, you remember that it has two parts. One part focuses on the number of nodes internally inside the community, and another part focuses on the number of nodes edges between communities. So here we have at the end of the first phase, we have this super graph where we only care about how many connections we have inside the community and outside the community. And we repeat this process iteratively. So then we also apply the phase 1 and phase 2 until our modularity value stops to increase. So this is basically the main idea, and I hope that at least some participants have chosen this greedy style approach or Louvain style approach for today's competition to optimize modularity. So if you optimize modularity, you then need to take care about the regularization part, and the regularization part is mostly about the density. So for this case, you should make sure that your communities are not too large enough. And now I will give you the most interesting and exciting part. I will talk about data sets. Today we had 3 graphs. The first one is a real world sparse graph. The second and the third graphs are artificial graphs. And the second graph is an artificial graph with well-defined communities. It means that it has very dense areas by construction. And the third graph is also an artificial graph, and it is structured as a lattice made of communities. So the density distribution inside the third graph is more natural. It is more, the density distribution is not too high. So if we compare the first graph and the second and the third, I would say that the first graph is sparse. The second and the third, on average, is also sparse. However, they have many dense parts. So it's better to consider them as dense graphs. And I will show you now some pictures. So here, how the first data set looks like. So it's actually a subgraph from the first graph, colored by a popular open source method to optimize modularity. You can see that almost all nodes are colored with one color, and we only have a few nodes that are colored differently. And you might ask a question why we also have this green or yellow and red nodes. So in my opinion, when we have this illustration, you should understand that this is only a part of graph, and probably the green node is connected to another part which is dense but not shown in this picture. So it can be colored differently. So here we also have a solution when all graph nodes are merged into one community. So from modularity aspect, it's a good solution, but we should also care about the regularization part because the density here is not so high. So from the regularization point of view, it might be more beneficial to separate this graph into 2 graphs and to increase the regularization part. On this picture, we have a dense graph in the right, and we have some also dense part. So we also see the gray colored edges. Gray color here represent an edge that connect 2 different communities. And now we will continue a slideshow. So today, during the live translations, you might have seen this kind of pictures. For example, on this picture, we also see a subgraph of the first graph. All these pictures are from the first graph. Here we also have a situation when we have a left part which is colored into one color, but the right part is not colored in one color. And as far as I remember, today we also have one contestant with a very similar situation. So my comment about this is the right part might be connected to some other subgraph, which is dense. However, we do not know it because we only see a subgraph. Sometimes it is easy to judge if a solution is good or not. Like here, we have a very dense area at the right and at the left and at the top, which are loosely connected. So we have only 3 communities here. Sometimes it is more difficult, like in this example, when we have a green colored community in the middle, which is probably not seen, but it is here. We don't know why it is present. Perhaps we also have another graph, and sometimes we just get this peculiar pictures. So all the previous pictures were from the first graph, and it was a sparse graph. Now let's discuss our second graph. So here is a subgraph of the second graph. So we constructed it artificially using the following method. So we directly constructed several dense areas in the graph, and we had some parameters about the density. So the density also had some normal distribution. So the exact density in every community is different, and also the exact size is different, and it is normally distributed. And then, so first we constructed these dense areas, then we connected pairs of communities by some random number of edges, which was limited to keep some density, not too high. So, and then we also added a random noise. So we connected random nodes together. So, and here we have our ground truth coloring. So this is every color represents the communities that we use in our construction. It is not necessarily optimal. However, it achieves high density. So the average density of a community here is probably the highest average density possible. However, it is not necessarily the highest modularity. And we also applied one popular open source modularity optimization method for this particular graph, for the second graph. And here we see that from modularity optimization point of view, at the left top of the figures, 3 communities are colored blue, and they were merged into one community. And of the same situation is at the top when we have 2 green communities which were merged into one. As I told before, modularity optimization itself has a feature of making communities large. So, for example, when from modularity optimization point of view, it may be beneficial to merge these 3 blue color communities into one, but you should also care about the regularization part, because the average density of community will decrease in this case. And now we have our final presentation part about the third data set, about the third graph. And during the live translations, we only see a small picture. Now I'm going to give you some details about the third graphs. Here, how it actually looks like. So the third graph is a lattice made of very dense areas of some maximal clicks. You may consider them maximal clicks from which we remove some edges. So if you look closely, you will see that the nodes of this lattice are very densely connected. It's not a maximal click. There is also some density, and there is also distribution of density. But this is our construction. We made a lattice, and we randomly connected some dense areas. So sometimes we can see some holes. It is natural because the connection is random, and the intersection between communities is random. And so, but actually, it is just the first step of our construction. Then we introduced a random noise to this graph. Because of random noise, it's hard to illustrate it, but I will try. So here is the baseline, and here is what we can get if we apply modularity optimization only to this particular graph. So you can see that modularity optimization has a tendency to merge many dense areas into one community. So the regularization for the third graph is also very important. Probably here we need to split some dense areas into we probably need to split some communities into sub-communities of different colors because it will increase the density. So as I said before, we added some noise, and here what we will have if we add some random noise to our graph. So here we added a little bit noise, and we also run some popular modularity optimization algorithm. When we add more noise, and because we add more noise, our illustration tool also tends to merge the graph nodes together. And finally, we add yet more noise, and we have this kind of picture. And in the end, our picture tries to collapse into one super graph, and here is our final coloring. So thank you for your attention. I hope it was exciting for you to participate in today's challenge, and see you next time.